Let's look at some more details associated with graphing trig functions. Over here I've drawn the graph of y equals sine x right here. And I want to take a look and see what the graph of y equal 2 sine x looks like. And I'm going to make a little table here of values between 0 and 2 pi in multiples of pi over 2. Well, so if I put 0 in for x, the sine of 0 is 0. I know that. I can see it right here on the graph. 2 times 0 is 0, so I end up with just 0 for y. So this graph, y equal 2 sine x, is going to go through this point on the x-axis. When I put in pi over 2 for x, the sine of pi over 2 is 1. I can see that from this graph right here. So the sine of pi over 2 is 1 times 2 is going to give me 2. So when x is pi over 2, this blue graph is going to be up here at 2. Now when I put in pi again for the sine, I get 0. 2 times 0 is going to be 0. So I'm back down here. I put in 3 pi over 2 for x, and the sine of 3 pi over 2 is negative 1. Negative 1 times 2 is going to be negative 2. And then when I put in 2 pi, I get 0 for sine x. 2 times 0 is 0 again. So you can see that the blue graph is going to drop down here to negative 2 and then come back up to 0. So if I sketch the graph of that, I'm going to get this. Okay, so you can see what happens with this 2 right here. It changes the amplitude of the graph. It doesn't affect the period at all, but it changes the amplitude. How about y equal negative 4 sine x? Well, if putting a 2 in front changes the amplitude, doubles the amplitude, putting a 4 in front is going to make it 4 times as big. So if I just looked at 4 sine x, I know my graph would go up to 4, down to 0, down to negative 4, and back up. But in this case, I multiplied all of those y values by this negative 1 right here, negative 1 times 4 or negative 4, either way you want to look at it. That negative sign changes all those y values to their opposite. So instead of starting here at 0 and going up to 4, it's going to start here at 0 and go down to negative 4, back up to 0. Over here it's going to go back up to 4 and then down to 0. So that graph is going to look like this. Its amplitude is 4 and it's reflected about the x-axis. Okay, I want to play an old tape I did a number of years ago that has to do with this same thing. Has a little graphing calculator things in there. It's the old TI-82, so you don't see those too much anymore, but the idea is the same. So watch this tape.
In this section we want to look at the kind of equations that change the amplitude and the period for the basic graphs that we looked at in the previous section. So what I've written over here is this: y equal a sine bx and y equal a cosine bx will have graphs that have amplitudes equal to the absolute value of a and periods equal to 2 pi divided by this number b. Now I'm going to assume right here that this number b is a positive number. A can be either positive or negative, and I just want to look at the absolute value of it, and that will tell me what the amplitude of the basic sine curve changes to, or the amplitude of the basic cosine curve changes to. What I want to do first is go to the graphing calculator and explain this in terms of some actual coefficients. Let's go to the graphing calculator now. Let me show you first of all what I have for y variables right here. My y1 is going to be my basic sine x curve. y1 is equal to sine x. For y2, I've changed this coefficient. It'll be 2 sine x, y3 is 3 sine x, and y4 is 1/2 sine x. So according to what I was saying previously, these numbers in front should give me a new amplitude for these graphs. I'll show you the window here. Goes from about negative 360 to positive 360 in increments of 90 along the x-axis, and y goes from negative 4 to 4. Here's the graphs. First of all, y is equal to sine x. Here's my basic sine curve. Y equal 2 sine x. You see it goes up to 2 and down to negative 2, but has the same period. There's y equal 3 sine x. Again, same period, but now an amplitude of 3. And here comes y equal 1/2 sine x. So you can see that that has an amplitude half of the previous amplitude. Next, what I want to do is go back and change another coefficient. This time, let's look at the y, go back to my y variables, and I'm going to change this to y equals sine of, let me move over here, 2x. And then I'll go down to my next one. I'll delete that coefficient, and I'm going to change this to y equal the sine of 3x. And then I'll go down again and delete this coefficient. And Did I get it all? No. And then go over here and graph y equals 1/2 sine of 1/2 x. I'm going to change my window to go from x equal 0 to x equal about 4 times, let's see, I want to go, how about x equal 720 degrees. That'll be twice 360. And let's change, I want to go down and change my amplitude or my y values from, go from -2 up to +2. Okay, let's look at these graphs. Y equals sine x. You see it goes through 2 complete cycles between 0 and 4 pi. There's y equal 2 sine x, y equal 3 sine x, and then y equal 1 sine of 1/2 x. So you see y equals sine 1/2 x goes through 1 complete cycle between 0 and 720, or between 0 and 4 pi. Let's go back and look at our y variables list. This coefficient in front of x right here tells us the number of complete cycles that the curve will go through between 0 and 2 pi. So on this graphing calculator, we see that this coefficient right here of x tells us the number of complete cycles that the graph of y equals sine x will go through between 0 and 2 pi, or 0 and 360 degrees on the x-axis. Let's graph this one by hand. According to what I wrote before and what I confirmed using the graphing calculator, this coefficient is 1, so this graph will have an amplitude of 1, and the period will be equal to 2 pi divided by 2, which is pi. So if this curve went through 2 complete cycles between 0 and 2 pi, then it goes through 1 complete cycle in pi units on the x-axis. So I'm going to label this with pi. Here I'll label this with pi over 2. This 1/4 of the way will be pi over 4, and right here will be 3 pi over 4. The amplitude is 1, so I'm just going to have my curve go up to 1, down to -1. It's a basic sine curve, so it starts at 0, goes up to 1, back down to 0, down to -1, and back up to 1. So this is 1 complete cycle of y equal sine 2x. The amplitude is 1, and the period is pi. So if I was to extend this to 2 pi, you see it would go through 1 more complete cycle, and there I would have 2 complete cycles between 0 and 2 pi on the x-axis. So that coefficient tells you the number of complete cycles the curve goes through in what was 1 period of 2 pi for the basic graph. So to find the period of the new function, we just take the old period 2 pi, that is the period of the basic sine curve, and divide by that coefficient 2. That gives us pi. Let's try another example. This time we have y is equal to 1/3 sine x. So that leading coefficient, or the coefficient in front of sine x, is 1/3. So that means my amplitude will be equal to 1/3. And my period will be equal to 2 pi divided by this coefficient, which is 1. So I just end up with the normal period of y equal of 2 pi units on the x-axis. So let's label this point 2 pi. Halfway between those two will be pi. Halfway between those two will be pi over 2, and between here and here, this should be 3 pi over 2. The curve will go up to 1/3 and down to -1/3. It's a sine graph, so it starts at 0, goes up to 1, or I should say 1/3 at the quarter point. At the halfway point, it's back down to 0. 3/4 of the way through the cycle, it'll be at -1/3, and then when I come to the end of the cycle, I'll be back to 0. So here is a nice, quick, accurate sketch of 1 complete cycle of the graph of y equal 1/3 x. So this coefficient right here changes the amplitude. This coefficient over here changes the period. Here's our next example. This time I have a cosine curve. My coefficient a is 1/2, so I'm going to have an amplitude of the absolute value of 1/2, which is 1/2, and I'll have a period of 2 pi divided by 3. So 2 pi over 3 for the period. So let me mark the x-axis, or first let's mark the y-axis. The amplitude is 1/2, so it'll go up to 1/2, down to -1/2. The period is 2 pi, so I'll just put, 2 pi over 3, so I'll put 2 pi over 3 right there. Halfway between 0 and 2 pi over 3 will be pi over 3. And then halfway between here and here, between 0 and pi over 3, will be pi over 6. So what I have is 1 pi over 6, 2 pi over 6, this will be 3 pi over 6, and then 4 pi over 6, which reduces down to 2 pi over 3. So 1, 2, 3 pi over 6 will be reduced down to pi over 2. Now it's a cosine curve this time, so it starts up at 1/2. A quarter of the way through the cycle, it's down to 0. Halfway through the cycle, it goes down to -1/2. 3/4 of the way back up to 0, and at the end of the cycle, it's back up to 1/2. So here's a nice accurate sketch of one complete cycle of the graph of y equal 1/2 sine 3x. It'll have an amplitude of 1/2, a period of 2 pi divided by 3, and it's a basic cosine shape. Let's look at our next example. Y is equal to 2 sine pi x, so this will have an amplitude. Whoops, can't spell amplitude. Let's abbreviate it, AMP. Equal to the absolute value of that coefficient, so that will be 2. The period this time is going to be 2 pi divided by this coefficient, which is pi, and so that ends up to be just 2. So an amplitude of 2 and a period of 2. So I'm going to mark on the x-axis then. It'd be nice I could actually probably do these equally spaced, but I won't. On the x-axis, that'll be 2. Halfway is 1. Halfway there is 1/2, and right here, 3/2. The graph goes up to 2 and down to -2. It's a basic sine curve, so it starts at 0. A quarter of the way through the cycle, it's up to 2. Halfway through, it's back down to 0. 3/4 of the way, it's down to -2. And at the end of the cycle, it's back to 0. A nice, accurate sketch of y is equal to 2 sine pi x. So this coefficient here doesn't have to be an integer. It could be an irrational number like pi. In that case, the new period is going to be 2 pi divided by this coefficient here, pi, so I end up with a period of 2. Now, I could have had equally spaced units on the x-axis and the y-axis so you could get a real good picture of what this looked like. This would be a good one to try on the graphing calculator and then use the trace button and see if we get at x equal 1/2, y is equal to 2, at x equal 3/2, y is equal to -2. If you do that, of course, you will get that on the graphing calculator.
Okay, so you can tell that video was shot a few years ago. I want to continue that last problem though and just extend the range over which we graph that function. So here we have y equal 2 sine pi x between 0 and 2. That's the graph that we just saw right there. Let's extend that so we get y equal 2 sine pi x between -4 and 4. Well, we can tell one period is 2 on the x-axis, so if I want to go out to 4, I'm just going to repeat this graph again. So let's do that. So there it goes out to 4. Now let's go the other way and have it go from 0 to -4. Well, it's going to come back down here like this, come back up there, up and back down. I can't draw too well this way, but I'll give it a shot. And then back down again, up, and then back down. So there's what the graph looks like between -4 and 4, and you can see I've got one cycle here. Here's another one. That's 2 cycles, 3 cycles, 4 cycles. So between -4 and 4, this graph goes through 4 complete cycles. Let's work a couple more problems. Okay, first we want to graph this equation, y equals sine pi over 2x. Well, I can look at this and see that there's a coefficient of 1 there, so my amplitude will be equal to 1. My period will be 2 pi divided by pi over 2. So 2 pi divided by pi over 2, let's see, that's going to be the same as 2 pi times 2 over pi. When I instead of dividing by pi over 2, I multiply by its reciprocal, 2 over pi. Those numbers divide out and I end up with 4. So for this graph, I know I'm going to have a period of 4. It's going to have an amplitude of 1 and it's a sine curve. So I can fill in the x-axis here. I'll go through one complete cycle in 4 units. That's 4, that must be 2, there's 3, and 1. Okay, let's draw a sine curve that does that. Start here at 0. At 1, it'll be 1. At 2, it'll be back down to 0. At 3, it'll be -1. And at 4, it'll be back up to 0. Connect those with a nice smooth curve, and I've got the graph of one complete cycle of this equation. So it should look something like this. Not too bad. Okay, Now here I have a graph, and what I want to do here is just from the graph identify the amplitude and period. So first of all, I notice that this graph goes up to 3 and back down to -3. So I know just by looking here that the amplitude for that graph is going to be 3. Now what's the period going to be? Well, the period is what it takes on the x-axis for that graph to go through one complete cycle. Well, let's see, here is one complete cycle. That seems to repeat itself again and again, and that happens between 0 and pi. So the period for this graph must be pi. Okay, so that's a look at graphing trig functions in relation to their amplitude, their period, and some reflections. Okay, we want to look at some more graphs here. I want to graph y equal 4 tangent x. And so over here what I've done is I've graphed y equal tangent x, and you know tangent x has a period of pi, and when I graph one complete cycle I start at 0 and then I go up to this asymptote right here that's at pi over 2, then I start down at the asymptote and come back up to 0. At pi over 4 the tangent is 1, because tangent sine over cosine, and pi over 4 being 45 degrees, sine and cosine of 45 degrees are equal, so tangent of that angle is 1. Same with tangent of 3 pi over 4, it's going to end up to be -1. So if this is the graph of y equal tangent x, what does the graph of y equal 4 tangent x look like? Well, that 4 is just going to multiply every one of these green y values that you see right here by 4. So where the graph was 0, it's still going to be 0 because 4 times 0 is 0. Where the graph was 1, now it's going to be 4. And as this goes up over here, each of these values is going to be multiplied by 4 also. Now down here, where this value of y was 0, 4 times 0 is still 0. This value of y is -1, 4 times -1 is -4. Okay, so that's going to be down here. So my graph is just going to be a lot steeper than it was. It's hardly even going to be able to tell the curvature of it, but it's still there. But in any case, that graph now is going to go up like this. It's hard for me to draw because it's so steep, but that's what it's going to do. It's going to look like that. If you were to zoom in on it, maybe shrink this down a little bit like that, you'd see more of that curvature that you get. It's still curved like that, but each of those values of y is multiplied by 4. Let's look at another problem. I want to graph y equal cosecant 3x here, and I know that cosecant is the reciprocal of sine, so I'm going to do a little bit of algebra here first. I'm going to write this as 1 over sine 3x. And so what I'll do is graph this function right here and then take its reciprocal. So the graph of y equals sine 3x, well, it's going to have an amplitude of 1, and the period is going to be 2 pi divided by 3, that coefficient right there. So if I want to graph y equals sine 3x, let's see, it'll start at 0, it's going to go out to 2 pi over 3, so let's call that 2 pi over 3. Halfway will be pi over 3. I guess that'll be pi over 6, half of that. 1 pi over 6, 2 pi over 6, 3 pi over 6, so that's going to be pi over 2. Okay, so my sine graph will start at 0, go up to 1, back down to 0, down to -1, and then back up to 0. So that graph is going to look like this. And I suppose I should label the axes right here. Okay, now let's go back to our original function, which is y equal cosecant 3x. Now I'm back here to this, and I'm saying, well, cosecant's the reciprocal of sine. Well, here's all the values of the sine function. They go between -1 and 1. Well, what's the reciprocal of 0? Reciprocal of 0, 1 over 0 is undefined. So I'm going to get a little asymptote right here. I'll just kind of draw that in. Same thing over here. When the sine is 0, its reciprocal is undefined. So I'll do that, and same thing over here. Okay, now how about here where the sine is 1? The reciprocal of 1 is 1. Down here where it's -1, the reciprocal of -1 is also -1. So let's see, the graph should come down like this, hit that point, and then go back up. Come up like this, hit that point, and then go back down. And when you think about it, when I'm in here, when I have a value of, let's say, 1/2 for y equals sine x, well, its reciprocal is going to be 2, so I'm going to be up here. The further down I get, 1/3, I'm going to get 3. 1/4, 4. 1/5, 5. All the way down here to 1/100th, that reciprocal is going to be 100. So as this graph comes down to 0, this graph goes off to infinity. So in any case, that's a look at the graph of y equal cosecant 3x. Let's look at some more graphs. Okay, this function is y equal 3 secant 1/2 x. So I did a little bit of algebra right here and just wrote the secant as the reciprocal of cosine. So the 3 stays out in front. It's 3 times the secant, so it's 3 times the reciprocal of cosine 1/2 x. Well, let's see, I want to just graph this function right here, and then I'll take its reciprocal, then I'll multiply by 3. So this function right here has an amplitude of 1 and a period of 2 pi divided by 1/2. 2 pi divided by 1/2, that's going to be 4 pi. Okay, so if I just want to graph y equal cosine 1/2 x, I'll label the axes this way. It'll start at 0, it'll end at 4 pi. Oh, this would be nice. So 2 pi is right in the middle, 1 pi, and then 3 pi. Okay, so if I graph that cosine function right there, I'll just do that in blue. Let's call that 1 and that -1, 2, and -2. Okay, so when I graph that, I'm going to get, it'll start at 1, go down to 0, down to -1, back up to 0, and then up to 1. So here is my cosine function. Okay, so now let's see what the graph of just secant 1/2 x looks like. Well, that's going to be the reciprocal of this blue graph. So let me get my red pen. And what I'm going to do is say, well, every time the cosine is 0, its reciprocal secant is going to be undefined. So that'll give me an asymptote. So I'm going to draw in the little asymptote right here, and then also over here. Okay, and then every time my cosine is 1, its reciprocal is 1. And when the cosine is -1, its reciprocal is -1. Okay, so I can draw that graph in. It looks like this. Okay, so my last graph then is going to be 3 times the secant of 1/2 x. Well, that's just going to take all of these red values of y and multiply them by 3. So where y is 1 right now, when I multiply by 3, let me just go up here, I'm going to get 3. Where it's -1, whoops, who did that? -1, that should be -2. And then I'll go down here, and that'll be -3. So where this was -1, when I multiply by 3, I'm going to get -3. Up here where it was 1, now it's going to be 3. Now all these other values are going to be multiplied by 3 also, so they're going to move up. All these are going to be multiplied by 3, and they're going to move down. So I should get a graph that looks something like this. I'm going to have the same asymptotes, and my graph should look like that. So the black graph is the graph that we want, and what we do is we break it down into individual steps. First, I notice that the secant is the reciprocal of cosine. That gives me cosine 1/2 x to graph. Okay, that's very nice because it turns out to be between -1 and 1, which means that taking the reciprocal is very easy. That's the red graph. Then the red graph is the graph of this, so all I have to do is multiply by 3 to get the graph I'm looking for. So I take all the red values of y, multiply them by 3, these all move up, these all move down, and I get the graph I'm looking for.